Okay, so continuing with the table we had, and I fixed the problem. It's 177, not 117, and I had it correct here. So I apologize for that. Okay, so out of 177 women with breast cancer, 132 they end up testing positive, and 45 end up testing negative. Now, if you remember from the previous slide, the 132 are the true positive, and the 45, these are testing negative, but they actually have the disease, and therefore we call them the false negative. Out of the 64,633, the majority, 63,650, are going to test negative, and those will be the true negative. However, 983 are going to test positive, and these are going to be the false positive. Therefore, if I want to calculate sensitivity, and you remember sensitivity, you only look at those that have the disease. So out of 177, how many tested positive? Well, the disease is 132. So 132 divided by 177 gives you 74.6%. So the test has a 74.6% sensitivity. It means its capacity of correctly identifying those with the breast cancer is 74.6%. So if a woman has a breast cancer, she has 74.6% chance of testing positive and about 25.3% testing negative. Yani three-quarter chances of testing positive and one-quarter chances testing negative. Looking at specificity, you only look at those that are healthy. So you're going to look at these, the large number of women, the 64,633. And as you can tell, really, really like a big portion were tested negative. And therefore, you take the 63,650 divided by 64,633, and you get a 98.5%. That is the specificity of the test. So this test has a very high specificity. If a woman is healthy, 98.5% chance she's going to test negative, and only 1.5% chance that she's going to test positive. But that 1.5% chance is big enough to cause a really big number of false positive. And therefore, when you come to calculating the positive predicted value, this time we're looking within those testing positive. So a group of women tested positive. In this example, 1,115 women tested positive. Now the question is, what is the probability for each one of them to actually have breast cancer? And the answer to that question is 11.8% only. So you realize just a woman testing positive in this example, we're going to tell her, well, there's still 90% chance that you're actually healthy, and only 11.8% chance that you have breast cancer, and therefore there is a need to do further testing. However, if we'll move into the negative predicted value, looking at the women that tested negative, 99, so taking this number and dividing it by the total, there is 99.9% chance that she's healthy. So women testing negative, we feel very much confident to tell her, well, we think you're healthy, you don't need to worry about anything. Of note, in this specific example, the prevalence of the disease, so if I were to take 177 and if I were to divide it by the total of both, it's going to be about 3 per thousand, which is quite rare. But this is just to serve as an example. So reliability and validity trade-off. Though we'd like to have a screening test with high sensitivity and specificity, this is not possible. There is always a trade-off between the two. The reason for that, or to be able to explain why there is this trade-off, we're going to use the following slide. In this example, we're going to use the test for blood glucose as a way to diagnose diabetes. So starting with the A graph, okay, And knowing that the red line are the diabetic patient and the orange line are the normal people, and knowing that you're looking at the blood glucose, the orange is the distribution of a blood glucose for the healthy individuals, and the red is for the diabetic. And you shouldn't be surprised that the red distribution is shifted higher than the orange distribution because they are diabetic. But nonetheless, they do overlap somewhere. Okay? And remember, when you test for diabetes, I should say for blood glucose, it's not whether something is present or absent, it's whether blood glucose surpasses a certain threshold. And therefore, you have to decide where's the cut point at which we start considering people to be positive and below which people are considered negative. So, in the first scenario, the threshold is put as low as possible. So the idea in graph A is to capture everybody that is diabetic. So not to miss anyone who's diabetic. Okay? And therefore, if you look here, the red shaded are the false negative, the orange shaded are the false positive. And in the graph A, we don't have any false negative. You're not missing anybody. You're capturing all of those that are diabetic, which is a good thing, but actually it's not, because look at the orange. You've captured a lot of people that are healthy and you've labeled them as positive. Because remember, when you're running the blood glucose, you don't know if the person is diabetic or not. All you're saying that if your blood glucose is above the limit, then you're going to test positive. And if your blood glucose is below the limit, then your test is going to be negative. And therefore, anybody who's above this black line right here, okay, then this person is going to be tested positive. And because the orange distribution, the healthy distribution, has a big portion of it that is above this dark line right here, you're going to end up with a lot of people testing positive, though they actually are healthy. So that makes us move into B, where now the black line has been moved a bit up so that it's somewhere between the two populations. So we have the population of diabetic people and the people and the population of healthy people. But what happens here is that though the orange shaded and the false positive will reduce dramatically, which is a good thing, unfortunately you start having a false negative appearing. So see the trade-off? You cannot reduce one of the two falses without increasing the other falses. So here we reduced dramatically the false positive, but unfortunately we start having false negative. And towards the last graph, where we're pushing the limit so that none of the healthy are testing positive, and therefore you do not have a false positive anymore, but you end up having a lot of false negative. Okay, so the purpose of this graph here is to show you that there's a trade-off between sensitivity and specificity. Okay, remember, one is related to false positive, the other one is related to false negative. And because most of the test is not just testing whether something is present or not, they're testing the quantity of that. مثلا, prostate cancer with PSA. We all have a certain level of PSA, but when that level of PSA reaches a certain limit, the test starts becoming positive. And therefore, where do you draw that limit? For blood, the glucose, the same thing. For blood pressure, where do you draw the limit for considering somebody to be hypertensive? The idea is the higher the limit is, the less false positive you're going to have, but you're going to get more false negative. And the lower limit is, the more false positive. Further illustrating the point, here I have Kamen, let's say this is the high blood pressure, and so hypertensive or not with blood pressure. This population is the healthy population up here, and this is the diseased population. And again, the distribution of the diseased is shifted toward the right more than the healthy, because normally they have a higher, let's say, blood pressure. And the black line is the cutoff above which you start labeling positive and below which you start labeling negative. So in the healthy population, the blue are the true negative because they're below the line. The orange are the false positive because they're above the line. In the diseased population, the yellow are the false negative because they're below the line, and the red are the true positive because they are above the line. And notice what happens as I move to the second slide. In the second slide, what I did is let me remove this just a second. Okay, so what I did is I moved the line a bit up. The blue area became larger, but at the same time, the yellow area became larger as well. Let me show that again. So I'm gonna go back one slide and come to that again. Okay, so it used to be like this. I move the line a little bit up, and I move it even further up, and you can notice that the blue area is getting larger and larger. Unfortunately, the yellow area is also getting larger and larger. And therefore, the true negative are you're getting more and more true negative, yani less and less false positive. But at the same time, you start having more and more false negative and less true positive. Okay? Again, the whole idea behind these slides is to show you that you cannot gain on both sensitivity and specificity. There is a trade-off. So how do we figure out the best trade-off? How do you figure out where is the best cutoff point to placing this cutoff, actually? Okay, so where do I place it? Well, there is something called the ROC curve, the receiver operating characteristic curve. What you do is you plot on the y-axis your sensitivity, and on your x-axis not your specificity, but your 1 minus specificity. And the reason you do the 1 minus is because the graph we want to plot, we want both to increase together. We just said a minute ago that as sensitivity increases, specificity decreases. So if I were to plot sensitivity versus specificity, I would get the opposite of this curve. And for purpose of making things easier to read, we're going to plot the 1 minus specificity. Okay? Now, notice that you get a square because the maximum for sensitivity is 1, that's the 100%, and the maximum for 1 minus specificity is also 1, that's 100%. The area of the square, its side times side, is going to be 1, okay? And usually they draw the diagonal, and basically the diagonal is showing you where things are, well, I'll explain that in a minute. So what you're going to do is, like I did in my previous slides, where I start changing the cutoff, and every time you change the cutoff, you're calculating a new sensitivity and new specificity. To explain that, I'm going to go back a minute. I'm going to go back to my slides, show you my slides, so that hopefully you understand. Okay, so going back 1, 2, 3 slides. So imagine for that cutoff point, I want to calculate the sensitivity. Remember, the sensitivity is actually the capacity of, so in a nutshell, it's this red area out of the total area. And you can see that sensitivity is quite large, maybe 90%. Okay? The specificity is the blue area out of the total area. So maybe here specificity is 70%. So you put it on the paper for the cut point of, let's say, 130 for blood pressure, you got a sensitivity that is 90 and a specificity that is 70. Okay? Then you change your cut point, you increase it. So now maybe I'm looking at a cut point of 135 for blood pressure. And I noticed that my sensitivity went down, maybe to 80%, but my specificity went up, maybe again for 80%. Then I changed the cut point. Maybe now the cut point is at 140. And I noticed that the red area now represents, out of the total area, maybe 60%. But the blue area represents maybe 95% of the total area. So by jotting down these values, And by calculating the 1 minus specificity, I can start drawing this curve, which is called the ROC curve. And hopefully, your curve is going to look like this. It's going to go up as much as possible to the upper left corner, and it's going to turn and start flattening up. That is a very good curve. It means that your test, whatever screening test you're using, is a very good test. And the way, if your curve actually is flat and close to the diagonal, then it means whatever test you're using is a bad test. Do not use it. It's not going to yield good results. If you're using multiple tests and you want to compare which one is the better test, then you do the ROC for each test and you compare them. The curve that has the highest curvature is the best. Now, how do we know the highest one? Well, what we do is we calculate the area under the curve. Now, remember, I mentioned a moment ago that the entire the entire square has an area of 1, okay? So the area under the curve, maybe in that example, could be مثلا 0.9 or 0.88. If you have multiple curves, the one that has the largest area under the curve will be the better one. So ROC curve first usage is if you want to compare different screening tests and you want to know which test is the better one. So maybe you have a test that is created by one pharmaceutical company and another one created by another pharmaceutical company, and you want to know which one is better. You can draw the ROC curve for both tests, and the one that yields the larger area under the curve would be the better one. So this is the first use of ROC curve. Another use of the ROC curve, which is actually why I talked about it, is finding where is the best cut point for starting labeling positive and negative. And basically what you need to do is you need to find the tangent to that curvature right here, okay? So by finding the tangent, which yields that point, that is going to give you the best ratio of sensitivity to 1 minus specificity, which is actually specificity, okay? So giving an ROC curve, you draw the tangent, finding that point is going to give you the best cut point that gives you the best ratio sensitivity to specificity. Now I'm going to try to see if I have multiple ROC curve as an example so that you understand what I'm talking about. Okay, so let's see if this one is, sorry, it's going to take a bit of time to open. Okay, so here are 3 ROC curves, and you're trying to figure out which one is the better one. Now, they're actually all weird, but you know, one is in pink, one is in green, and one is in blue. As I mentioned before, the closer you are to the diagonal, the worse the test is, and the higher up you are to the upper left corner, the better is the test. So here, if we're comparing test 1 to test 2 to test 3, it seems that the blue test appear to have the better ROC curve, and therefore you probably need to pick this one. Okay, let me see if I have another one that I can show you. Here's another one. All right, here's an ROC curve for only one test. Okay, and look, this is sensitivity, and it's 1 minus specificity, the diagonal curve, and it's curving up to the left corner, to the upper left corner, which is very good. Okay, and right here where it says max Uden index, where actually the tangent will be passing, so picking out this point right there is going to give you the best ratio sensitivity to specificity. Okay, all right, I'm going to see if I have anything more to show you. All right, maybe I should just go back to the lecture. Okay, so